Hello, everyone. In this lesson, we're going to talk a little bit more about continuity, which was introduced at the end of the limits lesson last week. So first, just a brief refresher of what it means to be continuous. Okay, so a function is continuous if the function is defined, right? So when you plug in your value of a, you get something there. Okay, the limit exists there. Okay, and the limit is equal to the function value, right? So when you follow the curve, right, towards that point, you end up where you expect to. Okay. Again, an intuitive definition of continuity is if you're looking at a graph, is that whatever your curve looks like, it's smooth, right? That you can trace it and not have to lift your pen or pencil off the page. Okay, so that's what continuous kind of means. So we're just going to briefly explore here some situations where you are not continuous. Okay, so in general, okay, there are three kinds of discontinuities that you can see in a graph. Okay, and you can probably think of a few that you've already seen before if you think about some of the types of functions you've worked with. Okay, so the first one should be really familiar. It's called an infinite discontinuity. Okay, and that's basically when you have a vertical or oblique asymptote. Okay, right? And it's called infinite, right, because your function goes off to infinity at that discontinuity. Okay, so that's what creates the break in the graph. Okay, the next type is called a jump discontinuity. Okay, this one is kind of new, although we did briefly talk about it in the last lesson. Okay, the idea is that the function has basically some kind of a jump where the curve is going along and suddenly moves to a different position. Okay, so in the last lesson, I briefly mentioned that Heaviside function, right? The power is off, and all of a sudden you flick a switch and it's suddenly on. Okay, so this is a jump right here. Okay, the function was going along smoothly, and all of a sudden it just ends up in another spot. Okay, so this type of a function has a special name. Okay, we call it a piecewise function. Okay, and I think that kind of says it all in the definition, right? My function has to be defined in different pieces depending where I am in the domain, right? Here, when I'm less than 0, I have one rule, and when I'm greater than or equal to 0, I have a completely different rule. Okay, so you probably haven't made a whole bunch of these before, right? Here's another rough sketch of what one might look like. Okay, but yeah, we're going to talk about that a little bit here. So for some reason, you have to define different parts of the function different ways. Okay, a key thing here, okay, if you can see here, I've left this circle open, right, to indicate that, you know, if this is at, say, 2, the function travels on this curve to 2, and then it continues here, but it's not actually at 2 where the circle is here, right? If this was filled in as well, then technically I don't have a function anymore, right? It would fail the vertical line test. Okay, so when you're lining that up, one of these can be solid, but not both. Okay, or if you have multiple pieces, only one of them can be solid there. Okay, the third type, which you encountered probably for the first time in advanced functions, is what's called a removable discontinuity. Okay, that's when you have a hole in the graph. So just to briefly review where that comes from, here's a function from, you would have seen, I guess, in the rational section of advanced functions. Okay, so first I note my restriction, right? X cannot equal 2. Okay, I'm going to start factoring this. So the top becomes 2 minus x, okay, and 2 plus x, and that's over x minus 2. Okay, I would like to be able to cancel this out. So a little factoring trick here. Okay, these two almost match, but they're flipped. So I'm going to rewrite that first one as -1 times x minus 2. Okay, over x minus 2. Okay, so now I can do my cancellation, divide that out, and I have negative times 2 plus x. Okay, so this would be negative x minus 2. Okay, so my function, after doing all that work, is really just the line negative x minus 2. Okay, so my graph would look something like this, where I have a y-intercept of -2, Okay, it goes in this direction, but okay, I said that x cannot equal 2. So at 2, I have to put a little break in here. I apologize for my wavy line there, but I have a hole, okay, because technically my function is not defined there. Okay. The reason we call this removable, okay, is because I can essentially patch that hole. Okay, I'm only missing one spot. So if I want to quote unquote fix my function here, so I'm going to patch the hole. Okay, is I'm going to redefine my function just a little bit. Okay, so I'm going to bring this back down here. Okay, so now I'm going to turn it into a piecewise function. Okay, so this is my f of x. Okay, and I'm going to say it's defined for this rule when x does not equal 2. Okay, and then where the hole is, well, I need to figure out where that point should be. So I'm going to briefly jump up to this part for a second. Okay, if I plug in 2, -2 minus 2, so that's -4. So if I want my function to work the way it's supposed to, I'll say my function equals -4 when x is equal to 2. Okay, and that has the effect of basically doing some, I don't know, mathematical spackle here and saying, oh, I want to put a point right there in the hole where I had the hole. And now my function doesn't have a hole in it anymore. Okay. Okay, and that's why it's called removable, because potentially you can fix it by doing a little adjustment to your function. Okay. So example 1, here's a piecewise function, and we're going to determine if the function is continuous at x equals 1. Okay. So first, let's just follow through with our rules. My first thing is, right, does f of 1 exist, right? Or is it defined? Okay, so when I go over here, okay, it says when I'm at 1, that would fall into the top branch there. So to evaluate f of 1, I know f of 1 equals 1 cubed minus 2, and that is equal to -1. Okay, so yes, it exists. Okay, my function exists here. Okay. Number 2. Okay, does the limit exist? So limit as x goes to 1 of f of x exist. Okay, so because I have two different things, okay, I'm going to have to look at the left hand and right hand limits separately. So I'll start with my left hand limit. So limit as x goes to 1 of f of x from the left hand side equals, okay, so again, my left hand side is that top part. So just to demonstrate it, I'm going to flip over to Desmos for a second here. Okay, so here's what my function looks like. Okay, and if I put a point on there and start moving along the left, okay, I get closer and closer to, looks like the point -1 and -1. Okay, and that's where I arrive because it's defined on this side. Okay, so the limit as I approach from the left-hand side is -1. Okay, so it's -1. Okay, again, we're going to get into this in more detail, but essentially, to test the limit, I can just go into my function and plug it in again. Okay, I can do, you know, it's -1, pardon me, not -1, right? It's 1 cubed minus 2, which is -1, okay, and that works here, okay, but it does arrive at -1. Okay, let's flip to the other side of the graph. Okay, as I go to 1 from the positive side, what is happening here? So again, I'm going to flip over to Desmos for a moment. Okay, this is the other side, so it looks like this. Okay, and as I approach here, okay, it does look like I'm getting closer and closer to -1. Okay. Now on Desmos, if I go right to 1, it says I'm undefined, right? Because technically, right, I do not have a point there. The limit on my domain is that x is greater than 1. I can't put in 1. Okay, but as I follow this along, it certainly seems to be approaching -1. It gets really close there. Okay. So it also approaches -1. So the left and the right hand side agree. Okay, therefore my limit exists, and this is good. Okay, third criteria. Okay, does the limit as x approaches 1 of f of x equal f of 1? Okay, and we don't need to write anything really down here, but we can see that's true. Right, my limit was -1, my function value is -1, therefore it is continuous at -1. Okay, and again, I'll look at the graph for a moment. If I put both pieces together, okay, yep, okay, they touch right there at -1. Okay, it has an interesting look to it because it isn't something bounces away, but yeah, it does connect there at -1. Okay. Example 2. So I guess this is an example of an area where a piecewise function kind of comes in. The cost of a data plan is listed below, where C is the cost in dollars and X is the usage in gigabytes. Okay, so it costs you $5 for anywhere between 0 and 10 gigabytes. Okay, it costs you $20 if you end up using between 10 and 50 gigabytes. Okay, and after 20, it's $1.50 per gigabyte. Okay, that's why this x minus 50 comes in. So I guess we just kind of did part A there, right? That's what's happening. This is $5 for the first 10 gigabytes. Okay, for the next one, it's $20 if you go between 10 and 50, so for the next 40 gigabytes. Okay, and afterwards, we're paying $1.50 per gigabyte. Okay, so we describe that in words. Okay, now we're going to sketch a graph of what it looks like. So again, I'm going to flip over to Desmos to help me with this. Okay, so the first part is a constant, right? It's 5, so it's just $5 anywhere between 0 and 10. Okay, after which it suddenly jumps to $20. So if you use, 10.001 gigabytes, you're suddenly going to find yourself paying 20 bucks. Okay, so this is the second part of our graph. Okay, is now it's 20, but it stays that way all the way to 50. Okay, after that, we start paying $1.50 per additional gigabyte. Okay, so now my cost just flies off there. Okay, so that's what my graph looks like, right? Broken up into pieces like that. Okay, so I've copied it over here. Okay, the final question was to identify any discontinuities. Okay, so the obvious one here, okay, is a jump discontinuity at x equals 10, right? There's a sudden movement from 5 to 20 at x equals to 10. Okay, another one I want to briefly point out, okay, this isn't super important in the grand scheme, but it will come up. If you want to get really technical, okay, the function is discontinuous at 0, okay, and this is for a reason that's not one of those 3 categories. Okay, at 0 because limit as x approaches 0 from the left of my function, this is c of x, does not exist. Okay, if you want to get technical, okay, it's discontinuous here because there is no left-hand limit, right? I cannot approach from the left side because there's no function on the left side of the graph. Okay, this one is not super important in this case because our domain starts at 0 and goes off. So it's not the end of the world, right? You can start your pencil here and go forward. But it may come up later in other things. So something to be aware of. Another example of that would be, say, your square root function, right? Okay, it looks something like this. So it's continuous everywhere. In a technical sense, it's not continuous at 0 just because the left-hand limit doesn't exist there. Okay. All right. So there's your information on discontinuities. Okay, and here's some practice work to help you follow up with that concept. Okay, some of these questions ask you, to sketch functions like the one I just did here. Okay, again, for the purpose of your homework, feel free to use Desmos for those if you want. Okay, some of the later questions ask you to just make up functions with certain conditions. Okay, it might be easier to draw those by hand, okay, and just draw a rough sketch of something than to try to come up with equations, right? So if it gives you equations to graph, feel free to use Desmos, okay, for the moment. But if it's just asking you to make something up off the top of your head, then it's probably easier to draw a rough sketch in your notes than try to make up equations and put them in Desmos. Okay, thank you for watching. And if you have any questions you want to take up, please send them along.